This is SpaceTime Series 27, Episode 145, broadcast on the 2nd of December 2024. Coming up on SpaceTime, what lies beneath the mysterious worlds of Uranus and Neptune, the final Venus flyby for NASA's Parker Solar Probe, and the most colourful map of the cosmos ever attempted. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study suggests that the ice giants of our outer solar system, Uranus and Neptune, feature layers of water, methane and ammonia, which, just like water and oil, don't mix. The findings could help explain the two outer planets' unusual magnetic fields, which have left scientists dumbfounded until now. See, until now, ideas like diamond rain and super-ionic water are the best explanations scientists have to try and explain what lies beneath the thick, bluish hydrogen and helium atmospheres of Neptune and Uranus. But now, Burkhard Miltzer from the University of California, Berkeley, has an alternative hypothesis, namely that the interiors of both these planets are layered, and that the two layers, just like oil and water, don't mix. Now, if correct, the idea reported in the Journal of the Proceedings of the National Academy of Sciences nearly explains the two planets' unusual magnetic fields and implies that earlier theories about their interior might be wrong. Miltzer argues that a deep ocean of water lies just below the cloud layers, and below that is a highly compressed fluid of carbon, nitrogen and hydrogen. And it's not just speculation. Computer simulations show that under the temperatures and pressures of these planets' interiors, a combination of water, methane and ammonia would naturally separate into two layers, primarily because hydrogen would be squeezed out of the methane and ammonia that comprises much of the deep interior. These immiscible layers would explain why neither Uranus nor Neptune have magnetic fields like that seen on Earth. That was one of the surprising discoveries about the ice giants made by the Voyager 2 mission during the late 1980s as it was completing its grand tour of the outer solar system. Miltzer believes that this new work provides a good theory as to why Uranus and Neptune have really different magnetic fields compared to planets like the Earth, Jupiter and Saturn. He says if other star systems have similar composition to ours, giant ice planets around those stars could well also have similar interior structures. Planets about the size of Uranus and Neptune, the so-called sub-Neptunian planets, are among the most common exoplanets discovered so far. As a planet cools from its surface downwards, cold and denser material sinks, while blobs of hotter fluid rise like boiling water. It's a process called convection. Now, if the interior is electrically conducting, a thick layer of convecting material will generate a dipole magnetic field, similar to what we see in a bar magnet. Earth's dipole field, created by its liquid iron outer core, produces a magnetic field that loops around the north and south poles and is the reason compasses point towards the poles. But Voyager 2 discovered that neither of the two ice giants has such a dipole field, only disorganized magnetic fields. And this implies there's no convective movement of material in a thick layer in the planet's interiors. To explain these observations, two separate research groups proposed more than 20 years ago that the planets must have layers that can't mix, thus providing large-scale convection and a global dipolar magnetic field. However, convection in one of these layers could produce a disorganized magnetic field. The trouble is, neither of these groups could explain exactly what these non-mixing layers were made of. Now, 10 years ago, Miltzer tried to resolve this problem repeatedly using computer simulations. In his simulations, he used about 100 atoms with a proportion of carbon, oxygen, nitrogen and hydrogen reflecting the known composition of elements in the early solar system. Now, at the temperatures and pressures predicted for the interior of planets like Uranus and Neptune, that's some 3.4 million times Earth's atmospheric pressure, 4,750 Kelvin, he simply could not find a way for these separate layers to form. However, all that changed last year thanks to the development of machine learning. Miltzer was able to finally run a computer model which simulates the behavior of 540 atoms, and to his surprise, he found that the layers do naturally form as the atoms are heated and compressed. It shows that the water had separated from the carbon and nitrogen. Now we know why these layers form, one which is water-rich and the other which is carbon-rich. And in the case of Uranus and Neptune, it's the carbon-rich system which is below. The heavy part stays at the bottom and the lighter part stays at the top, and it cannot do any convecting. And the amount of hydrogen squeezed out increases with pressure and depth, forming a stably stratified carbon-nitrogen-hydrogen layer, almost like a plastic polymer. While the upper water-rich layer likely convects to produce the observed disorganized magnetic field, the deeper stratified hydrogen-carbon-rich layer can't do this. When Miltzer modelled the gravity field produced by a layered Uranus and Neptune, the gravity fields match those measured by Voyager 2 nearly 40 years ago. Miltzer predicts that below Uranus's 4,800 kilometre thick atmosphere lies a water-rich layer about 8,000 kilometres thick. And below that, a hydrocarbon-rich layer, also about 8,000 kilometres thick. And its rocky core will be about the size of the planet Mercury. Though Neptune is more massive than Uranus, it's actually smaller in diameter, with a thinner atmosphere, but with similarly thick water-rich and hydrocarbon-rich layers. Its rocky core is also slightly larger than that of Uranus, approximately the size of Mars. The proposed NASA mission to Uranus could provide confirmation if the spacecraft has an onboard Doppler imager in order to measure the planet's vibrations. You see, a layered planet would vibrate at different frequencies than a convecting planet. Miltzer's next project will be to use his computational model to calculate how the planetary vibrations would differ. Needless to say, we'll keep you informed. This is SpaceTime. Still to come, the final Venus flyby for NASA's Parker Solar Probe, and a new NASA mission to make the most colourful map of the cosmos ever attempted. All that and more still to come on SpaceTime. NASA's Parker Solar Probe has completed its final Venus Gravity Assist flyby manoeuvre, passing within 376 kilometres of the Venusian surface. The flyby adjusted Parker's trajectory into a final orbital configuration, which will ultimately bring the spacecraft to within an unprecedented 6.2 million kilometres of the solar surface later this month. It'll be the closest any man-made object has ever flown to the Sun. And although the Sun is the primary target of the Parker Solar Probe mission, its Venus flybys have become a boon for new Venusian science. That's all thanks to a chance discovery by WISPR, the probe's wide-field imager. The instrument looks out from Parker and away from the Sun to study fine details in the solar wind, the constant stream of charged particles flowing out from the Sun. But on July the 11th, 2020, during Parker's third Venus flyby, scientists turned WISPR towards Venus in the hope of tracking changes in the planet's thick cloud cover. But the images revealed an amazing surprise. A portion of the WISPR data, which captures visible and near-infrared light, seemed to see all the way through the thick clouds to the Venusian surface below. Scientist Naomi Eisenberg from the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, says the WISPR cameras looked through the clouds to the planet's surface and saw that it was actually glowing in the near-infrared because it's so hot. Venus is sizzling at approximately 465 degrees Celsius, and this was radiating through the clouds. The WISPR images from the 2020 flyby, as well as those from the next flyby in 2021, revealed Venus's surface in a new light. But they also raised some puzzling questions, and so scientists used the November flyby to help answer them. The Venus images corresponded well with data from the Magellan spacecraft, showing dark and light patterns that line up with surface regions which Magellan captured when it mapped Venus's surface using radar between 1990 and 1994. But some parts of the WISPR images appeared a lot brighter than expected, and that's hinting at extra information captured by the WISPR data. So that begs the question, is WISPR picking up on chemical differences on the surface, where the ground is made up of different material, or is it seeing variations in age, where more recent lava flows added a fresh coat to the Venusian surface? Eisenberg says that because it flies over a number of similar and different landforms than the previous Venus flybys, the November flyby provided more context, allowing scientists to better evaluate whether WISPR can actually help distinguish physical or even chemical properties on the Venusian surface. After the flyby, Parker was on a course to swoop down close to the solar surface, the final objective of this historic mission first conceived more than 65 years ago. Parker's data will be charting as yet uncharted territory. In this hyper-close regime, Parker will quite literally cut through the plumes of plasma still connected to the Sun. It'll be close enough to pass inside solar eruptions, sort of like a surfer diving under a crashing wave. The closest approach to the Sun, perihelion, will occur on December the 24th, during which Mission Control will be out of contact with the spacecraft. So we won't know what happened until December the 27th, when Parker will send a tone beacon. Hopefully that'll confirm its success and the spacecraft's health. Parker will then remain in this orbit around the Sun for the rest of its mission, completing at least 2 more perihelia at the same distance. This is SpaceTime. Still to come, making the most colourful map of the cosmos ever attempted. And later in the science report, Russia has commenced using a new nuclear-capable hypersonic missile in its attacks on Ukraine. And we'll have all the details available on this new weapon. All that and more still to come on SpaceTime. A new NASA mission slated for launch next year will make the most colourful map of the cosmos ever attempted. NASA's SphereX's mission won't be the first space telescope to observe hundreds of millions of stars and galaxies when it's launched in April next year, but it will be the first to observe them in 102 colours. Although these colours aren't visible to the human eye because they're in the infrared range, astronomers will be able to use them to learn more about the physical characteristics which govern the universe less than a second after its birth 13.8 billion years ago. SphereX will also allow scientists to learn more about the origins of water on planets like the Earth. Principal investigator Jamie Bock from NASA's Jet Propulsion Laboratory in Pasadena, California, says it'll be the first mission to look at the whole sky in so many colours. And whenever astronomers look at the sky in a new way, they can usually be counted on to make new discoveries. Short for spectrophotometer of the history of the universe, epoch of reionization and ICE's explorer, SphereX will collect infrared light, which is wavelengths slightly longer than what the human eye can detect. The telescope will use a technique called spectroscopy to take the light from hundreds of millions of stars and galaxies and separate that light into individual colours, in the same way a prism can transform sunlight into a rainbow. The colour breakdown can reveal various properties about an object, including its chemical composition, its distance from the Earth, even its heat. You see, what human eyes perceive as colours are actually distinct wavelengths of light. The only difference between colours is the distance between the crests of the light wave. Now, if a star or galaxy is moving, its light waves get stretched or compressed, changing the colours they appear to emit. If it's moving away from the observer, those light waves are stretched and the colours appear slightly redder. That's called redshifting. If the object's moving towards the observer, those colours are compressed and appear slightly bluer. That's called blue shifting. It's actually the same Doppler effect you get in sound waves, which is why the pitch of an ambulance siren seems to go up as it approaches you and lower as it moves away. Astronomers can measure the degree to which a light is red-shifted or blue-shifted, and they can use that to infer the distance to the object. SphereX will apply this principle to map the exact position of hundreds of millions of galaxies in 3 dimensions. By doing so, scientists can study the physics of inflation. That's the event which caused the universe to suddenly expand by a trillion times in less than a second just after the Big Bang. This rapid expansion amplified small differences in the distribution of matter. Because these differences remain imprinted in the distribution of galaxies today, measuring how galaxies are distributed across the universe can tell astronomers more about how inflation might have worked. Now, SphereX will also measure the collective glow created by all the galaxies near and far. In other words, the total amount of light emitted by galaxies over cosmic history. Scientists have tried to estimate this total light output by observing individual galaxies and then extrapolating that to trillions of galaxies across the universe. Trouble is, these counts are leaving out some faint or hidden light sources, such as galaxies that are too small or too distant for telescopes to easily detect. And with spectroscopy, SphereX can also show astronomers how the total light output has changed over time. For example, it may reveal that the universe's earliest generation of stars and galaxies were producing more light than previously thought, because they were more plentiful or bigger and brighter than current estimates suggest. Because light takes time to travel through space, we see distant objects as they were in the past. And as light travels, the universe's expansion stretches or redshifts them, changing its wavelength and colour. Scientists can therefore use SphereX's data to determine how far light has travelled and where in the universe's history it was released. SphereX will also measure the abundance of frozen water, carbon dioxide and other essential ingredients for life as we know it along more than 9 million unique directions across the Milky Way galaxy. And this information will help scientists better understand just how available these key molecules are in forming planets. Research indicates there's a lot of water out there in space. But most of the water in our galaxy is in the form of ice rather than gas, frozen to the surface of small dust grains. In these dense clouds where stars form, these icy dust grains can become part of newly forming planets, with the potential to create oceans just like the ones we see here on Earth. The mission's colourful new view of the universe will enable scientists to identify these materials because chemical elements and molecules leave a unique signature in the colours that they absorb and emit. Many space telescopes, including NASA's Hubble and Webb, can provide high-resolution in-depth spectroscopy of individual objects, even small sections of space. Other telescopes, like NASA's now-retired WISE Wide-Field Infrared Survey Explorer telescope, were designed to take images of the whole sky. But what SphereX does is combine all these abilities into a single spectroscope looking at the entire sky. By combining observations with telescopes that target specific parts of the sky with SphereX's big picture view, scientists will get a more complete and a more colourful perspective on the universe. This report from NASA TV.
Astrophysics is much more than just capturing different wavelengths of light. Many objects or phenomenon are simply too far away to directly image. A lot of data comes from pixel-sized point sources, and those points provide astrophysicists with a powerful window into what makes up the universe. Even now, most of what scientists learn about the cosmos comes from studying light. Astronomers can work out distances, speeds, sizes, temperatures, and the composition of elements because matter behaves in predictable and consistent ways. They do this by literally prying these photons apart. This is spectroscopy. Spectroscopy is the study of how matter interacts with light. And it all began with a prism. Light entering one side of the prism bends or refracts as it passes through the triangle shape and exits out the other side. All of the wavelengths enter together, but they exit as a rainbow-like spread of colors. What's happening is that the shorter, more energetic wavelengths, like blue and violet, bend a little more than the longer, lower energy light, like red and orange. Because they bend at slightly different angles, the wavelengths separate, fanning out into a band of colors. NASA has a whole fleet of telescopes that can split and study a wide range of light on the electromagnetic spectrum, not just the light that our eyes can detect. So Hubble can detect through the visible spectrum, but also a bit into the infrared and the ultraviolet. Webb is just infrared and can look at the light that is emitted from billions of years ago. And of course, the images from Webb are really spectacular. This spectrum shows the light that penetrated the atmosphere of a planet called WASP 96b. The light being measured comes from the planet's host star, some of which skims through the atmosphere. Humans are a long way from directly imaging exoplanets, so telescopes like Webb will use spectroscopy to find those chemicals that could support life in their atmospheres, which is why Webb's first spectra is so amazing.
Bumps and wiggles that indicate the presence of water vapor in the atmosphere of this exoplanet.
But it's one thing to identify single elements or simple molecules, but deciphering whole foreign bodies
took us a very long time to figure this out. It really took us many decades, and it took us many fantastic new instruments.
If all of our astrophysical objects or anything that we're looking at were made up of one element, this would just be so easy, but we don't. So we have to do experiments on Earth to prove what we're looking at looks like what we are thinking we're looking at. So here is argon. It glows this really pretty purple. And then if we look at it with a spectroscope, it shows us a very specific fingerprint to argon. These are called spectral tubes. They contain the gas of one element, and the box runs a voltage through the tube. When I turn on the switch, the charged gas turns to plasma and emits a color that is unique to that one element. It also makes unique lines when you look through the spectroscope. This same process happens in a star or a hot region of gas. So we use tubes like this to verify what we see in space. If you do a quick search for spectroscopy data, there are numerous ways that the data can appear. Those variations are based on the source of the cosmic light. There are 3 types of spectra that we can use: continuous, emission, and absorption. Light from a hot, dense source, like the sun, produces a continuous spectrum. When that light passes through cooler gases on its way to us, the gases take away or absorb some of that energy. Dark lines appear where specific colors are missing. And when thin gases glow themselves, we see only their characteristic colors, kind of like a cosmic barcode. Like all data, there is an art to analyzing spectra. Scientists use computers to calculate and tease out clear signals, comparing them then to models that are already known.
Many scientists in the labs on Earth, they try to recreate the same conditions and measure basically what these fingerprints of those different transitions for different elements are.
Okay, so we're always comparing to sort of the fingerprint of what we have, and then if it has deviated from that, that is the new information from what we're looking at.
Correct.
Spectra unveil the structures of black holes, the swirling winds that surround them, and those big jets of particles that come out of them.
So all of this is mostly accretion disk at this level. It's just different parts of it. We can zoom in, right? And we see all of the absorption lines, right? All of these lines are also shifted a lot. So they come from this wind. So that's how we know that there is winds blowing around black holes.
The same principles apply no matter the wavelength of light. But each wavelength of light tells us a little something different about each character we find in the universe. It's pretty wild how different the universe looks to our eyes and how it presents to our telescopes. And that's precisely why we need to observe in different wavelengths of light. Modern astronomy is built upon spectroscopy. So with every stream of light we gather, we further understand what the universe is made of. All we need to do is pry open its contents.
This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. Russia has commenced using a new nuclear-capable hypersonic missile to attack Ukraine. This is a major escalation of Moscow's invasion of Ukraine because it demonstrates a new unstoppable capability, giving Vladimir Putin a significant strategic advantage over the West. The new missile, called Oshenk or hazel tree in Russian, flies at over Mach 10, 10 times the speed of sound. That's more than 3 kilometers per second. And it can maneuver mid-flight, thereby making it harder to track and intercept using existing state-of-the-art air defense systems. You see, speed's important because the faster a missile can travel, the quicker it gets to its target, and the less time air defenses have to react. Ballistic missiles fly in an arcing trajectory, first going up into outer space and then back down to their targets. But as it descends, a hypersonic missile gains so much extra speed and kinetic energy, it can maneuver down towards its target, avoiding interception. Until now, 80% of all Russian missiles fired into Ukraine were intercepted by Patriot batteries. But these new hypersonic ballistic missiles negate that advantage. In other words, as of today, there is no means of counteracting such a weapon. Now, from what we can tell, Oshenk carries up to 6 MIRVs, multiple independently targetable warheads, and they can be either conventional or thermonuclear. The missile's use against Ukraine showed numerous warheads striking simultaneously in a spectacular show of force. And of course, it wasn't just to damage Ukrainian territory. It was meant to show the West what Moscow is now capable of. In other words, the bear was saying, don't mess with us. Now, in this case, they were conventional warheads, but they could just as easily have been nuclear. Ukrainian media claims the missile was launched from the Kapuskin Yar rocket range. That's around 900 kilometres from its target in Dnipro. Vladimir Putin described the missile as being medium range, but Russian military experts say it's actually intermediate range, meaning a range of up to 5,000 kilometres and just one level below that of an intercontinental ballistic missile. That means the Orshink could hit any point in Europe, Eastern Asia or the Western United States. The US Defense Department are describing the Orshink as an experimental missile based on Russia's RS-26 Rubzik, which itself is a modified Topol ICBM. Now, Moscow has announced that it's approved full production of the new missile, and that implies only a few prototypes are available for use at the moment. But as Russia tools up and begins production, that will change. And in the process, it will also change the global balance of power, bringing us all a lot closer to a potential third world war. Turning to other news now, and the Lancet's annual stocktake on how climate change is impacting global health has shown that almost half of the world experienced extreme drought last year. The study found that health threats posed by climate change continued to grow, and it affected more people in 2023 than at any previous time in history. The authors say 48% of all land areas around the world experienced extreme drought. And people globally are now being exposed to an average of 50 more days of temperatures that threaten their health. The report is the 8th of its kind, and the researchers say the findings are the worst yet. Well, last week it was the stunning discovery that the wheel was likely invented in what now is Israel. Now scientists have unearthed what could be evidence of the oldest alphabetic writing in human history in a tomb in neighbouring Syria. Archaeologists from the Johns Hopkins University discovered the writing etched onto finger-length clay cylinders dating back to around 2400 BCE. That's some 500 years earlier than the previous known alphabetic scripts. The new discovery upends what archaeologists know about where alphabets came from, how they shared across societies, and what that could mean for early urban civilizations. The discovery was made at an archaeological dig site at Tel el-Mara in western Syria. Carbon-14 dating was used to determine the age of 6 human skeletons found in the early Bronze Age tomb. The cylinders were among a range of objects buried with the occupants, including gold and silver jewellery, cookware, a spearhead, and intact pottery vessels. Previously, scholars had thought the alphabet was invented in or around Egypt, sometime after 1900 BCE. A new documentary about the royal family's secret passion for UFOs and the paranormal has just been released. The doco, titled King of UFOs, speaks with witnesses about the late Queen and Prince Philip's passionate interest in topics like crop circles and the Rendlesham UFO case from 1980, often described as the British Roswell. It suggests that a UFO landed in the forest at Rendlesham over the Christmas weekend in 1980, not far from RAF Brentwaters, which at the time was a US Air Force NATO base. Airmen from the base who went to investigate reported seeing strange orbs and beams of light shining through the forest. Now, apparently the most likely source of this light wasn't a flying saucer, but the nearby Orfordness Lighthouse. Tim Mendham from Australian Skeptic says the Royals have a long fascination with all things paranormal.
We've known for some time, actually, that Prince Philip had a bit of an interest in UFOs and that sort of thing, but I didn't know, actually, that the late Queen also shared his view. This is the theory that comes up in a recent documentary, which is looking at the royal family's interest in crop circles and UFOs and all that. What apparently happens is that they had a lot of books, they discussed things with different people, they investigated, all according to this documentary anyway. Particular event, a Rolls-Royce turned up at a crop circle, and the people in the circle said, oh great, we're going to get Queens turning up, but it wasn't. It was just supposedly the royal family's scientific advisor who was coming out to have a look. I don't think the Queen necessarily made a royal visit to a crop circle. One of the problems with this is that the fellow who made the documentary named Mark Christopher Lee...
If you've got a name like Christopher Lee, you've got to be in the supernatural, sure.
I know. He said that the royal family had to keep this mostly a secret because of possible ridicule, but if such high-standing, balanced people took them seriously, why can't we? And I trying to figure out what necessarily makes a royal a high standing, but balanced people, and are they necessarily more intelligent or more incisive than anyone else? I would suggest not, especially if the royal family has a strong penchant for homeopathy, which is a very dodgy, that's actually a false medicine. It just does not work and it can't work, and it's one of the areas that the skeptics will be 100% sure that nope, ain't nothing there. But anyway, so these high-standing, balanced people are believers in a totally pseudo-medicine like homeopathy, and yet their belief is supposed to be endorsed because of their standing in UFOs and crop
circles. It's like getting celebrity endorsements for your political beliefs, isn't it? You know, why would you believe anything a celebrity tells you? They're an actor.
Yeah, why would you believe celebrities for anything? You know, a medical treatment, a product, a vacuum cleaner, you name it. Why is just because you know them and they look nice doesn't mean they actually understand the technology or the implications of what they're endorsing. I know the whole concept of celebrity endorsement, whether it's a royal family or a film star, is pretty difficult actually to support. Why not support someone with actual expertise, like a scientist? Could have a scientist, because all scientists.
That's a radical idea.
That's a totally radical idea. Yeah, why ask someone who's an expert? Why not get a film star who's been in an action movie?
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.